Thanks very much for being here. It's nice to see all of you here today. So today we gather to celebrate and honor Rosemary's career and her contributions to our school. Let me start our day together by acknowledging the people of the Kulin Nations on whose lands we gather today. I want to pay my respect to elders past and present. Wominjeka, as you probably all know, is the traditional greeting of the Wurundjeri people. And it is an invitation, an encouragement to come together with a purpose, to enter a space with a purpose. And I think that's a very welcome start to our workshop today, because our purpose is to celebrate and thank you, Rosemary, for all your hard work in education and research for our school. Very often our busy schedules leave us way too little time to actually step back and reflect on our individual accomplishments and on our joint accomplishments, and to focus on what we enjoy in our demanding careers as academics, or even just to get together as we do now, speak to each other and learn from each other without constantly thinking in the back of our minds about the next item on our to-do list. So I'm very pleased with the format that Rosemary has chosen for her day. She has invited colleagues and friends to speak about the science they enjoy, and this allows us to celebrate what is important to us as a community. It reminds us of why we are all here in this school, to advance our knowledge and to learn from each other and together. And this format is a testament to Rosemary's dedication to make our school a better place over the years. So before we get started now with our exciting program, Michael Morgan will say a few words on Rosemary's contribution and impact over the last decade. Thank you, Michael.
It is my privilege to be asked to say a few words about our colleague, Dr. Rosemary Mardling. Rosemary is a larger-than-life character whose presence in the school has enriched it immeasurably. Rosemary's connection with physics and mathematics goes back many years, indeed decades. She completed her undergraduate and postgraduate studies at Monash, including her doctorate in 1992 under the supervision of Professor Joe Monahan and also Professor Kevin Westfold in the then Department of Mathematics. In 2015, when the school amalgamated with our astrophysics colleagues in the School of Mathematical Sciences, I remember a chance encounter with Rosemary near the Maths building. She told me that she was considering joining the new school, particularly in view of the vicissitudes she had experienced as a female academic at Monash. I remarked that I hoped the school would provide her with a new beginning. I'm very grateful that Rosemary decided to join the School of Physics and Astronomy. She has been an important influence in shaping the school's culture, and we are a better place for her presence. Every department needs a Rosemary, someone who is fiercely independent and voices her concerns when they see an injustice or lack of equity. Rosemary has been a vocal advocate for women in the school. She shaped the school's first Equity, Diversity and Inclusion Committee and organized the school's first culture survey, forcing us to examine for the first time the assumptions that underpin a male-dominated academic environment. Rosemary is also an outstanding educator. I've enjoyed the occasional discussions with her about what makes a good teacher. An expression that Rosemary often used was, yes, but do they have physics in their bones? Rosemary does have physics in her bones, and indeed mathematics. She's a self-confessed junkie. Self-confessed science junkie. And someone who loves doing research, but on her own terms. Her approach to academia is echoed in a quote by the British-American astrophysicist Cecile Payne-Gaposchkin. You do not undertake a scientific career in quest of fame or money. There are easier and better ways to reach them. Undertake it only if nothing else will satisfy you, for nothing else is probably what you will receive. Your reward will be widening of the horizon as you climb, and if you achieve that reward, you will ask for no other. Those qualities are reflected in Rosemary's research and in her teaching. In the latter, Rosemary exhorted students to achieve their potential, particularly encouraging women and disadvantaged students to aim high. I'm grateful to Rosemary for providing a learning environment with a high level of intellectual rigor, but one that was always accessible to students. This view is reinforced by her colleagues, whom I asked to describe Rosemary. What came across from these responses were the high standards she sets, the care she shows her students, and the way she's inspired students who supervised. And of course, the passion she's exhibited for mathematics and astronomy. That passion is easily testified by, if you've ever attended a colloquium, you'll always hear Rosemary asking questions. No, indeed, her other interests, I won't go into them, but she has interests in music and also at the science-art interface. Rosemary, I wish you the very best in your retirement and hope that you have more time to spend doing research and perhaps revisiting the Saint-Michel Observatoire in the south of France. It's noteworthy that the coat of arms of Saint-Michel features a figure holding a sword in one hand and scales in another. This nicely encapsulates Rosemary, who in her time at Monash, I think, fought for justice and aspired to a fair, more equitable workplace. I'd like to finish with a poem by Sarah Haag titled Relativity, which I hope might encapsulate something of Rosemary's spirit as a researcher at Monash. When we wake up brushed by panic in the dark, our pupils grope for the shape of things we know. Photons loosed from slits like greyhounds at the track reveal light's doubleness in their cast shadows that stripe a dimmed lab's wall. Particles no more, and with a wave bid all certainties goodbye. For what's sure in a universe that dopplers away like a siren's midnight cry? They say a flash seen from on and off a hurtling train will explain why time dilates like a perfect afternoon and predicts black holes whose parallel lines will meet, whose stark horizon, even starlight, bent in its tracks, can't resist. If we can think this far, not our eyes adjust to the dark. Rosemary, I'd like to personally thank you on behalf of the school for all that you've done and your many contributions at Monash. Please join with me in thanking Rosemary.
That's a hard act to follow. Yeah, go on.
Yeah, but our next speaker is some of you might have known him.
You know, one of the things women are criticised for is crying at the drop of a hat. You brought tears to my eyes. Thank you, Mike.
That's all right.
Even a poem at the end. Wow. It's fabulous. Gee. Okay. And I've got to hold put this on. Put them on the desk, but you know, I like to dance around and stuff. Yeah, well, I'll give it a try. And is my beautiful friend Andrea here? Oh, gravitational chemistry. Andrea is the professor of is a professor of chemistry here at Monash, and you know, when you write a talk, you might. I bet you all find that you have somebody in mind. I mean, I had a few people in mind, but I especially had my beautiful Andrea in mind. Daring to talk about chemistry, I mean, in the gravity context. So we'll find out what the hell gravitational chemistry is as we go along. But I want to sort of tell the story from, well, the PhD start, and I'm very happy to see my PhD supervisor here, Joe Monaghan, who thinks in a very particular way that suited me perfectly. He likes to understand things back to the essence, to square one, to understand things deeply, to strip a problem back to its bare minimum without throwing the baby out with the bathwater. So he inspired my way of thinking, and well, he's part of the story. So and you're going to respond, computer? No, Stevie. It's not responding. I'm pushing return, I'm pushing arrows. Okay. Oh, yeah, I clicked the thing, there you go. So I'll tell the path to grave. So, you know, having retired, oh, there's another beautiful friend down the end who's just flown down from Sydney, Ursula DeMarco. Thank you, darling. Yes, so retiring has given me the chance to focus on what I love best. It's my art, as I'm sure it is for many of you, and it's, you know, a big advantage of getting to my age to have saved up enough in superannuation to be able to be paid as an artist to do her thing. So the thing I'm currently obsessed with is, well, we'll see what it is, but in the end, gravitational chemistry, but here's the path towards it. So, yes, I started my thesis with Kevin Westfold, who very few of you will know, but certainly Michael, sitting in the front, is old enough to know who he was. He put me on the problem of the emission mechanism from pulsars. Well, that problem's still not solved, so luckily I didn't get going with that. He became Deputy Vice-Chancellor and didn't have time for me, and that was a damn good thing, because I went started again with Joe Monaghan. And he put me on the problem of the binary tides problem, and at the time, this is in the 80s, there was a lot of hype about chaotic systems, and Joe asked me to think about how the non-linear interaction between modes, and could it be modes of oscillation of a star with a binary companion. Of course, with a nearby companion, the star will oscillate like anything will if you kick it. And so, of course, I started, the very first thing I tried to do was reproduce some of Joe and Bob Gingold's results. And it was just a simple set of differential equations that govern this thing, and so I set it up, and I couldn't reproduce the results, and I tried, and still I couldn't. And I was thinking, well, I'm probably not really cut out for this job. I can't even get past square one. But then it occurred to me, well, maybe the system's chaotic. That is, exquisitely sensitive to initial conditions. So I tested that hypothesis. I changed one of the parameters by 10 to the minus whatever you like, 10 to the minus 7 or something, and sure enough, it was chaotic. And here's a plot from one of the papers that resulted. And you start at, here's the eccentricity versus time, essentially, and the two paths follow each other for a bit. They're almost the same initial conditions, but then they diverge. And so that was a relief and a fascinating discovery. At the time, I got my first little baby who's sitting in the front, Kate, and before I'd written up, I thought, oh, I really should, finish my thesis before I go around having a family, but then I just couldn't, I can never wait. I want it, and I want it now, my family always said. So I got myself a little Kate and managed to write up my thesis miraculously. Well, she was a good sleeper, so that helped. And then by the time I graduated, I was 8 months pregnant with my son, Paul, and so after that you would think there'd be really chaos in the Mardling-Thompson family, but luckily my husband, Mark, is one of the most supportive husbands you could ever wish for, and with the added bonus that I could discuss my ideas with him. And he was my sounding board. And so I realised, and Joe had already mentioned that this problem was important for this thing called tidal capture, and I realised I could apply my discovery to this problem. So the idea is that in a dense stellar system like a globular cluster, stars, the stellar density is high enough, and very crucially, what we call the velocity dispersion, the relative velocity of stars is low enough such that when stars come close to each other, well, not so close, but they actually, their relative orbits are nearly parabolic. And so if they come close enough at periastron, they can raise, some of the orbital energy can be transferred to the tides of the star and actually make the binary bound. So this is called a tidal capture binary, and it was really important back then. This is the 90s, but actually in the 70s, when X-ray astronomy really got going with the first satellite telescope and so on, the Einstein Observatory, I think it was called. Frank's online. Is Frank online? I don't know. It was the hot thing, this was before cosmology became the hot thing. All the top guys at Cambridge and elsewhere were thinking about why these dense stellar systems had so many X-ray sources. It was proposed that tidal capture formed these very close binaries, so they're called low mass X-ray binaries. Oh yes, it says there. These are very short period binaries composed of a neutron star and a normal star accreting onto the neutron star, and it emits copious X-rays. And they could see that there were many, many more of these things in globular clusters per unit mass than in the field. So dynamics was a key. So it was hot, hot, hot. I applied my discovery to this process, published a couple of papers on it, and immediately zoomed into the stratosphere of, you know, rock star in astrophysics. So the contrast with Monash couldn't have been greater. It was amazing, because here I was, well, I won't say how I felt, but Kate knows what I always call it. But anyway, so that was fantastic and exciting, and there were conferences around the world asking me to come and speak, with sessions, whole sessions organised around this new idea. And the reason why it was important, I won't spend so much time on every slide, but this is such an interesting story, I think it is anyway. People thought that after a tidal capture binary is formed, that it would circularise so quickly, that is, the energy would be dumped into the star so quickly that the star would be destroyed. So how could you have an X-ray binary in the end? Well, this thing that I discovered showed that actually there'll be this short chaotic phase, and after that it'll just slowly and gently circularise, and the binary won't be destroyed after all. So that was the beginning. Okay, so I want to trace this path to gravitational chemistry and the essence of the physics behind what's going on. So here are two systems, almost identical. The second one is the star at periastron, they're a little closer. And one is stable and one is chaotic. So what does that mean? Let's see. So we'll see the stable one, nothing much happens. The energy transferred to the star doesn't build up. The orbit hardly changes, it rotates a bit. But the chaotic one, the energy transfer process is random. Sometimes it dumps a lot of energy, sometimes it takes it back, and effectively it's a random walk. And see, it just took it all back in that example there. So, okay, that's an example of a chaotic system. Now, people at the time realised that actually there's probably an even better way to make these close binaries in dense stellar systems, and that is through 3 and 4 body interactions. For example, 2 binaries which come close together, they have a much bigger cross-section than just a single star, and as we'll see later in some animations, they can do some pretty fancy stuff. And there's been a revival of this problem these days, because the gravitational wave community are very interested to know how, or the origin of these very close black hole binaries and black hole neutron star binaries that end up merging and emitting the gravitational wave signals that we see. Okay, so the 3-body and 4-body problem were seen to be of interest. Here's an example, very similar to what we just saw before, but replacing the star with a binary. So these are triples, and again we see that the stable triple, a little bit of energy is transferred through periastron, but then it just goes back to how it was. Whereas in this case, we see the orbit is, you know, growing, shrinking all over the place. Energy and angular momentum are transferred between 2 subsystems, the inner binary and the outer orbit, we'll call it the outer binary. So both of these systems are chaotic, and they're clearly very similar systems. Physically something's similar, even though these are just point masses, but whereas before we had a fluid star. And again, well, he's stable versus chaotic. The butterfly effect, the extreme sensitivity to initial conditions. I start two systems with, you know, change the initial separation by 10 to the minus 7 or whatever you like, and we see that the stable system, you can't even see the red curve here, but here they diverge and have very similar behaviour. And I was going to say, you know, one of the amazing things about these chaotic systems is, you know, I could give you my code and you put it on your computer and you'll get a completely different answer. Like, what? So I became obsessed with understanding why that was true. What's really going on? I do wonder though, if we both had bought a new, you know, Apple Mac Air or something, and they were supposed to be have identical processors and everything, and we should do the experiment one day. I don't know. So I wondered if the physical origin of chaos in triples and close binaries is the same, and yes, it is. It's nonlinear resonance between the subsystems, the inner binary and the outer orbit, or the star with the oscillations and the orbit in those two cases. So using this idea, so based on physical principles, the idea of resonance, internal resonance, I formulated a simple stability criterion which is used across astronomy, and especially these days it's been rediscovered for the gravitational wave people. So I'm very proud of that. And my collaborator, Sfera Arseth, was built these in-body codes to model a system like a star cluster. And he's, you know, and of course you've got the evolution of computers over this story as well. So of course they were much slower back then. If a triple formed in the simulation, the integration would grind to a halt almost, because the time step of the integration would be governed by, well, is governed by the shortest period of, you know, shortest orbit. And so he needed to have a robust stability criterion in the code, so that if he discovered, or if a stable triple was formed, it wouldn't just you know, use up all the CPU, and it could sort of be put to sleep until later on. So one of the things that intrigued me about all this chaos stuff is that a system is either chaotic or it's not. What is going on? What is the difference between physically? What's the difference? This is a series of in-body integrations, just triples, where I vary the outer eccentricity and the period ratio and keep other things constant. And I plot a red dot if the system's chaotic, and how you judge that's another story. But you can see an interesting sort of fractally structure to the boundary, and I really wanted to be able to predict that analytically. So using the ideas, well, okay, the two-body problem is integral. One of the keys to these ideas is that for chaos in mechanical systems, if you have a series of subsystems that are integrable, I guess formally they don't have to be, but it certainly helps the analysis if they are. And the three-body problem, at least the hierarchical version of it, and note that the outer body orbits the centre of mass of this pair. What was I going to say? Yeah, well, so it's the coupling between two-body systems, if you like, and it's the interaction energy, or the interaction term, that holds all the secrets to stability and chaos and the evolution of the triple and so on and so on. So this idea of nonlinear resonance is fundamental, and of course Poincaré started these ideas 100 years ago. So here's a beautiful example, just quickly, the double pendulum. You know, you can't get much more stripped back than this, and it turns out that the three-body problem and the other one and many other problems, effectively have pendulums at their heart in some sense, in some abstract sense. So pendulums are nonlinear oscillators, and a key to the story is that the frequency of oscillation depends on the amplitude. So a linear oscillator, that's not true. It doesn't matter how much you stretch it out, the frequency of oscillation will be the same. And also pendulums can librate or circulate. That's part of the story, which we haven't got time to go into, but fundamental. A single pendulum's integrable, but if you join two together, of course, well, not of course, but if you've ever seen a real one do this. Now, you know, so this is a card, if I started the initial conditions differently, we'd get different behaviour, but just, it looks pretty basic there, but all of a sudden it flips over. Why? You know, like, I never get sick of it. And that's what I would tell students. You know, I'd teach the same classes year after year, and I would tell them I never get sick of what I'm teaching you. It's so beautiful. This is a key word for today's symposium. So, okay, I did work out how to characterise this boundary based on some ideas that were already out there but not applied to this more complex system, and it's to do with resonance. These are the resonant boundaries in inverted commas, and where they cross over it predicts the stability boundary. So that's very beautiful. So before I get back to gravitational chemistry, I wanted to say a quick word about some of the papers, some of the work I've done that have had a big impact on astrophysics. And I should say, you know, I didn't publish enough papers to be promoted, it seems, in this system. If I'd stayed in the maths department and been compared to mathematicians, that may have been a different story, because my record certainly compares to some of the best over there. But nonetheless, that's how it is. I was just, as Michael very nicely, you know, painted the picture of me, and I'm stubborn and I only want to work on problems that I find almost too hard. And otherwise I'm just bored. So I chose to well, I would say not sell my soul to the devil and work on things I found boring. This is an example of a piece of work that, you know, took a lot of intricate and time and so on. I reformulated celestial mechanics so that it could be both simpler to use and also, very importantly, applicable to arbitrary configurations. So celestial mechanics was formulated for the solar system. The mass ratios, the planet to star mass ratios are small, the eccentricities tend to be small, orbital inclinations are small, and so, you know, it was designed to study that system. But the exoplanet systems, or indeed these fancy stellar systems, have arbitrary, you know, architecture, if you like. And so this allows one to really, you know, get out of that box. And a nice example of other people using it is studying the existence of Planet 9, which involves very eccentric Kuiper belt objects that appear to be almost kind of lined up and suggest there may be a planet somewhere else. They needed to use this kind of formulation to study it analytically. Another couple of examples that have, you know, made a big impact. One was bringing back tides, how to couple together tidal interactions in a body or planet system. That's used throughout the exoplanet community to do that kind of modelling. And this one, I'll just tell my daughter that this paper, my beautiful aunt, who died at age 93 last year, 1 year ago, yesterday. And she used to read the newspaper, and she would look up you know, if there was a thing about astronomy, she'd cut it out and say, Ro, look at this. So one day she did such a thing. And I thought, oh, gee, I didn't know that. That's really interesting. And I went away and thought about it, and I thought, oh, I did a little bit. Anyway, this paper resulted, and it's one of my most highly cited papers. One of the things I pride myself on is not just having a nice mathematical formulation, but for allowing it to be accessible even to observers. So observers love this paper as much as the theorists. Here's a nice series that is very happy that I've retired, because they're all almost finished, the old academic, they're almost finished, but they really are. And they are waiting for me to finish this other stuff I'll tell you about today. But just this system, you know, the Kepler Space Telescope discovered, like, it just blew our minds. Another example of nature saying, aha, you thought you understood this problem, but systems of planets that are wafer thin. If we observe the solar system from afar, we wouldn't see all the planets transiting if we happen to see one, if we even saw one. But these systems, you see, I think the record is 8 planets in what we call a resonant chain. So it's a relaxed, non-linear system titled dissipation. So these planets form out of a disk, and they tend to migrate towards the star. And because it's a non-linear process, and because there's dissipation connected with this migration process, the system tends to relax to special configurations. And indeed, there are many of these, you know, the period ratios are in these beautiful commensurabilities. And the thing, I mean, Andrea looks like an atom, right? You know, these are like atomic orbitals, and I'm the physicist here, with these kind of, you know, quantumish structures, period ratios, whatever. Anyway, so that's waiting for me to come back to it. So now some fun. Getting back to gravitational chemistry, I'm going to show you some nice little numerical integrations. But the aim of my current work, and I've reached the aim, but is to be able to describe these kind of interactions analytically, to understand back, you know, the physics and what's really going on, and the parameter dependence and the scalings and so on. Okay, so let's let them move. Now we're in the frame of the centre of mass of the system. 2 binaries come together and they swap companions. They come back together again. This is called a resonant interaction. And a pair hop off. One of the important points about this is how close that pair is in the end. You know, the gravitational wave, people want to be able to understand how very close binaries form. And they looked at dense stellar systems for the right environment for this, and this is the kind of interaction they would be interested in. We see, and actually, well, okay, they were reunited, they were pulled apart to start with, that's cool. When I did this particular simulation, I thought there was something wrong with the integration, because this yellow one just sat there. Gee, why isn't it moving? And sure enough, no energy and angular momentum, perfectly, you know, conserved. It just had lost all its linear momentum to the other bodies, like almost all. Incredible. Love it. Okay, and most of the time the intermediate steps are hierarchical, as I sort of described before, and are amenable to the study I want to tell you about. Here's an example. We're a bit slow. Tight binary formation. Well, we sort of saw a tight binary. Look, it's super, super close. We'll zoom in a sec. That little yellow and red pair, extremely tight and very eccentric actually, binary, which in reality, if they're close relative to their size or the gravitational radius, for, you know, if we put some GR in there, this would be an important interaction. Here's an example of a triple forming from a binary-binary collision. There's a resonant interaction, a lot of mucking around, but here's the triple coming. Well, it's not going to stay that way for forever. And I think, oh, this one's, you know, does nature do this? I don't know, but I could put the initial conditions so that it does this. Makes a little tight pair in the middle. These guys come back and take their partners back, and off they go. And you can see that it's perfectly symmetric. It's very nice. And so there's a lot of, yes, analogies with human interactions in these things. Okay, one more. This is a slingshot. Well, we've seen slingshots, but anyway. Zip, zip, zip. And there's another tight little pair and some slingshots. Yes, they're lots of fun and very beautiful. You know, people who are not scientists often ask, well, if you really understand something, doesn't it take the beauty away? But we all in this room would say, no, it doesn't. It makes it even more beautiful to understand the essence of things. So, of course, so getting back to chemistry, just like in chemistry, the thermodynamic environment really matters. What kind of reactions can you have? Well, it depends on the thermodynamic environment. So at the centre of a globular cluster, I would say that it's a cool environment because the velocity dispersion, the relative velocities of the stars are, you know, relatively low. And by low, I mean, you know, a few kilometres a second, 10 kilometres a second. The Earth goes around the Sun at 30 kilometres a second, for example, which is kind of fast, but in the scheme of things here, it's kind of slow. On the other hand, at the centre of a galaxy, near the, you know, with a massive black hole at the core, the stellar velocity dispersion up to, you know, thousands of kilometres a second. So that makes it very hard for some of these interactions to occur, just as it does, just as, you know, in normal chemistry, if the gas is too hot, you're not going to get nice molecules forming. So wouldn't it be good to be able to study this, not just within body stuff, but have an analytic setup that allows you to do it? I'll just say briefly that gravitational focusing, I sort of mentioned that before, is really important in this problem. You need to get the stars really, or binaries really close together, and that's, if the velocity dispersion's low, you can get these near parabolic orbits. We'll skip past that. So we want to understand how these small n systems are formed and destroyed during scattering events, how this depends on the thermodynamic environment, how their stability depends on the state of the system. I love that concept of the state of the system, and so on. And we want to be able to efficiently do the statistics of reactions, work out cross-sections and so on. These kinds of studies are really expensive numerically, and people usually resort to Monte Carlo studies, but you know, it's very hard to completely, you know, cover the parameter space when the number of parameters is high, and you know, it's bad enough for a 3D triple where there are 9, and there are many applications for this. So yeah, that's what I've kind of been saying. We want to be able to see the scaling laws and the parameter dependence and so on, and you don't want a great big messy mathematical thing. You want something that your brain can do something with. And in fact, historically, the kinds of expansions that were available, and including the Hamiltonian methods, which are beautiful in their own right, but they tend to shroud the physics in often unnecessary complexity. So my new, well, actually it's not really new, I've been working on it on and off for many years, and I get distracted by another problem or by life or by also teaching or new rules from the university about Moodle or whatever. But, you know, quantum mechanics, I really wanted to do theoretical physics when I was a baby student. And like many students back then, we sort of, you know, were a bit, oh, I don't know if I want to be in this department, sorry, Michael. And so a lot of us, including boys, went across to applied maths. And that's where we were. But quantum mechanics, and Mira knows this, Mira and Jesper's lecture notes, their recent lecture notes are made in heaven. In my kind of lecture notes, this is the way I always like to do my lecture notes, and you know, I'm learning even more from them. Anyway, there are various concepts from quantum mechanics that make their way into this formulation and it's all very beautiful. So, okay, here's a great big equation, but I want to try and, for those who, you know, think about mathematical things like this. So this is the paper that's, again, nearly finished. It's in 3D. It uses these, you know, Wigner rotation matrices and various things, but it gathers together, you know, people have tried to do this problem for a long time, they, you know, with varying success. But, you know, they end up with unwieldy, great big messy stuff, and it's sort of hard to or off-putting to use, you could put it that way, I guess. But this formulation, and usually they're just doing up to quadrupole or whatever, this is, you know, to arbitrary degree, whatever you feel is necessary for your problem, and involves these spherical harmonic, you know, indices and so on. But these special functions, which I got approval from my Kate to call origami functions, because I'll show you, they neatly fold up. I mean, there's a lot of parameters and things in this problem to take account of, but you'll see they very neatly fold up. This is just the sort of, you might call, linear term that people had come up with before. Well, part of it they'd come up with before, but this involves also the back reaction and these non-linear terms, which turn out to be really important because the important ones are phaseless. You see, there's, you know, okay, there's different L's here, but when they're the same, this thing does not depend on phase. And it turns out for the decay of triples, for example, this phaseless term is really important. I'll show you in a sec. And from this you can get the eccentricities and the inclinations, very beautiful. You get the tilts as a scatter happens and so on. For both the inner and outer orbits, you can use conservation of energy and angular momentum. And how well does it work? Well, pretty damn well, I think. So I'm showing here that red is the n-body integration, the black is the analytic that I just showed you. And if you leave out that phaseless term, you really get it wrong. This is for strong interactions. So these systems can come very close, even go through each other, which is kind of weird that it works as well as it does, given it's a spherical harmonic with the small parameters, the ratio of outer periastron to inner semi. But nonetheless, so this is the change in energy through a scatter. This is periastron here at t equals 0. This is the change in eccentricity. And here's a couple more examples. Here's a polar example. Tilt the two orbits to 90 degrees. And it does well with the change in the inclination and the node, the line of nodes. And there's a completely retrograde one, and you can see that the interaction is quite different and involves a higher frequency interaction. But from this, you can see exactly why things are happening. And at its heart is resonance, resonant transfer of energy and angular momentum at periastron. Here's my little origami functions. Talking Rosemary is, get out of the way, off my duck, my swan. But anyway, these things fold together all the different information, the tidal coefficients, you know, mass ratios, length mass ratios, these beautiful inclination functions, very simple expressions. And the phase dependence, there's lots of angles in this problem, but they all come together there. And then the piece de resistance, the physicists love their overlap integrals, and so do I. And these really are describing resonant interaction. And they depend just on two parameters, so you can tabulate them and use them for very efficient scattering experiments. And I'm probably going over time, but I'll try and, now it doesn't even want to, yeah. There's these, you know, again from quantum mechanics, you're used to this idea of wave packets and transferring energy for all the different harmonics and so on and so on. And just one little thing from this, notice how the frequency drops through during passage through periastron, and this is nonlinear resonance and a big part of the story. I can strip back that fancy thing I showed you before just to the quadrupole term, for example, and with such a simple expression I can do cool things like work out the distribution of decay lifetimes. If you have a decaying triple, how many outer orbits does it take before the outer body escapes? Well, it's a statistical distribution. It and it follows this very beautiful idea from statistics, first passage time and so on. No time to go into it. This is, you know, a bit crappy here and a bit crappy here. I've stripped it back to almost nothing, and with a bit more information in there, it might do even better. Quickly, stripping it back even further to just one single term, it turns out that this system, if I treat all, here's the unpacking the origami a bit here. Here's one of these inclination functions. There's the half angle there, familiar. It turns out that that stripped back system contains the essence of the chaos, and in fact it's identical to the standard map, a well-known mapping which exhibits chaotic behaviour for different values of this parameter A. And this is the last science slide, just to say, okay, we're looking at four-body or binary interactions, but most of the time, really, it's like a binary plus the centre of mass of the other thing, and you can use this analysis to understand or predict what's going to happen. It certainly can't do the details of a resonant interaction, but it can predict that it's that it's a possibility. In other words, that you can pull the binary apart, and we can see, you know, each successive thing is a change in the initial phase. So obviously, what happens depends on the relative phase of periastron. Sometimes we get excitation, de-excitation, and so on. It's all there. Okay, so I think my last picture is a picture of, this is Kate again. There is no Duvel in the bottle. I had already drunk it all, but nonetheless, it's up here because of the cheeky, defiant look on her face, and for the quote from Albert Einstein that imagination is more important than knowledge, and ain't that the truth?